and then zoom. In case there's an error.
Recording in progress.
All right, everybody. We're starting 10.1. I'm sorry about the delay. 10.1 is on hypothesis testing. Let's say we are in class and I ask you to draw a card 6 times from a deck of cards. We saw in chapter 5, decks of cards have half red cards, half black cards. And every time you draw the card, you replace the card, shuffle it back up, so you have the same probability, 1/2 every single time. If you draw red, the class wins 2 extra credit points. But if you draw black, you're going to have extra problems on your review for the final. And here we go. So you end up drawing 6 black cards in a row. Even though the red cards were the reward, you drew 6 black cards in a row, and you're starting to wonder, is your teacher a snake? Is he a card shark? Has he been hustling you? And you start doing some calculations, and you recall from probability, drawing 6 blacks is like the first card equals black, and the second card equals black. And then there's a lot of ands, so ands turns to multiplication. The probability of each was 1/2, and you end up getting about 1.6%. So in 1,000 trials, you would expect to see 6 black cards in a row, maybe 16 times. And as you know, this is possible, but it's highly unlikely. So you have 2 possible outcomes. I'm either really lucky, I managed to hit that 1.6%, or 2, I've been using a stacked deck against you. You never had a chance of winning, and you've been conned. This is the idea of hypothesis testing. What we do is we make an assumption about reality. We assume something's going to be true, usually based on previous evidence or information. Then we are going to gather sample evidence and analyze the result to see if it contradicts our assumption. Now, when you started drawing the cards, you didn't think there was any dispute, but as soon as you started drawing too many black cards, you start going, is this still true? Is my assumption that the deck is half black true? Because that's what the assumption you've made. When you're drawing cards, you're assuming you've got a fair deck of cards, half are red, half are black. So the probability of getting a black was half. And so you go, is my assumption true? We do gather the evidence. We drew 6 cards. You analyze it, and we got a low result. And depending on how that result ranks is how we determine whether or not we support our hypothesis or not. This is the idea of hypothesis testing. The hypothesis, I'll go into that more in a bit. For now, we're going to focus on one population parameter. When we're talking about a statistic, it's for data. When we're talking about a population thing, it's a parameter. So these are like the statistics, the mean, the proportion, standard deviation, variance, things like that. So, give you some examples. The percentage of milk fat in California dairy milk in 2012 was 3.72%. I know, I looked this up. Researchers believe that a change in diet has changed the percentage of milk fat content. What parameter is this statement talking about? What is the claim? Well, they're talking about a percentage. They're talking about a percentage. Percentage is usually proportion. So it sounds like they're talking about the proportion of milk fat. The claim is that it's no longer the same. It's changed, which means that the claim is that it's not 3.72% anymore. That's the claim. The old claim is that it's 3.72%. The new claim is that it's not. It didn't say higher or lower. It just said not. This is an interesting thing. I teach in Tulare when I'm in person, so a lot of these are agriculture based. For every inch increase in standard deviation of plant-to-plant spacing for corn, the corn grain yield drops approximately 2.2 bushels per acre. A new corn planting machine revealed at the World Ag Expo claims it has decreased the standard deviation below that of its former model, which had a standard deviation of 4.5 inches. What parameter is this statement about? What is the claim? Well, it's saying, the claim says it's decreased the standard deviation. So we must be talking about standard deviation. We're not talking about proportion or mean. We're talking about standard deviation. And they are saying that it has decreased, or it is now lower than 4.5. They don't say how much lower. Could be 4.4. Could be 2.1. Okay? And this is a real study. Information is 2.2 bushels. I made up the World Ag Expo thing, but the 2.2 bushels thing was from Purdue. And then one that you guys might be familiar with. The average final exam score for statistics students was 73%. We believe the use of computers in statistics courses has increased the average grade students receive on their finals. Like StatCrunch. That's what I'm talking about here. Don't use it StatCrunch. What parameter is this statement talking about? It says the average final exam score, and it mentions an increase in the average. Average is another word for mean. So this is talking about the mean for statistics students on their final exam. The claim is that even though it used to be 73%, the use of computers has made it higher, so that the mean is now higher than 73%. I got a tickle in my throat. Excuse me. So these are all just examples of what kind of problems you're going to see. Hypothesis testing is a procedure that uses probability and sample evidence to choose between two hypotheses. We're going to have the null hypothesis, and we're going to have the alternate hypothesis. So the null hypothesis is the previous claim, basically. It's the one we're going to assume to be true. And we denote it with an H sub 0 like this. It's also called H naught. So H naught or H 0. This indicates this hypothesis is where there's no change, there's no difference. It comes with an equal sign. H naught has an equal sign in it. You're going to see in a second. Fuck. The alternate hypothesis is the competing claim. We usually denote it as HA, but sometimes you'll see H1 or HA. Okay? I think the 1 goes with the H0, like 0 and 1. A stands for alternate, though, and 0 means old. So let me clear that. The alternate hypothesis is usually the claim we're trying to support. It has an inequality sign in it. So we will see less than, greater than, or not equal. Those are the ones we're looking for. Okay? Okay. Clear that out. Close that. There we go. So let's look at the ones we had before. H naught, the way the claims are listed, we say H naught, we list the parameter, and we say what the value is, and then HA, we list the parameter, and we show what the value is. This was from the milk fat problem. So the information said that it used to be 3.72%. As a decimal, that's 0.0372. And so the null hypothesis is about the old claim, that it was equal to 0.0372. 0372. And it said researchers believe the claim has changed. So it says non-equal. This is called a two-tailed test. Although I don't test you on the names of like two-tail or one-tail. I'm just saying it so when you see it, two-tail is the not equal to test. And notice I list both H0 and HA, and I list the parameter, in this case proportion, both times. H0 is always an equal sign. HA is the other sign. Then we have the left-tailed test type. Here, this is the standard deviation problem with the corn. And the claim was that they've lowered it below the 4.5. So standard deviation is represented by sigma. Sigma is less than 4.5 is the new claim. The null hypothesis is the old claim. So it's equal to 4.5. This is called a left-tailed test. And an easy way to remember it is pretty much the arrowhead. This little less than sign looks like an arrowhead pointing to the left. Okay? So that's a easy way of remembering it. Left-tailed test. It points to the left. Then we had a problem on the mean for final exam scores for stat students. The old mean was 73 points. And the claim was that using StatCrunch or other computerized software has raised the final exam score. So mu has gotten higher. The mean is higher. And again, if you make an arrow, this looks like an arrow pointing to the right. So this is called a right-tailed test. Okay? In all three of them, H0 has the equal sign and HA does not. Okay? So the null hypothesis, we've all seen court shows, law shows. It's like not guilty. It's what we assume to be true until proven otherwise. We assume the null hypothesis is true. It's usually the old information or the given information. And the alternative hypothesis is much like the statement of guilt. The defendant is either innocent or the defendant is guilty. Okay? That's the two options in a court of trial. The defendant is either innocent or guilty. But we don't say innocent or guilty. We say not guilty or guilty. We're going to talk about that in a little bit. But the alternative hypothesis is usually the one they're trying to prove, just like a lawyer or prosecutor is trying to prove guilt in a court of law. Even though we say guilty or not guilty, we never actually declare the defendant innocent. The reason why is we never have 100% information if they are innocent. It's just evidence points towards innocence or not guilty. The only way we could be 100% sure is in a court of law, have video footage and the entire jury witness the crime. In terms of statistics, the only way we would ever have this guilty or not guilty being innocent is if we ask the population, the entire population, the question. We're only asking a sample of the population, so there's always that little bit of doubt. Maybe we just asked the wrong people kind of thing. So since we don't ask everybody, it can only offer strong evidence against the null hypothesis. If we asked everybody, we'd be 100% certain, but we wouldn't have a hypothesis test at that point. That's a lot of work, though. So there's two outcomes of the hypothesis test. We can either reject the null hypothesis, which means if the null hypothesis is true, it would be surprising. This is the case with the example I gave you at the start of this lecture. Your teacher has a deck of cards and is offering you a chance to draw cards, and you assumed the probability was 1/2, but then you got some evidence that said maybe it wasn't. So rejecting the null hypothesis would be that case. You're rejecting the null hypothesis. You're rejecting that the deck is fair. Failing to reject the null hypothesis, if it's true, it's not surprising. So if we had that and you drew 3 red cards and 3 black cards, it wouldn't be any surprise because half the deck is red and half the deck is black. And so the way we say it is when we're doing it, and we'll do examples of this with every problem we do, there's either sufficient evidence to support the claim or there is insufficient evidence to support the claim. And there's variations on this wording, but this is, if you follow this pattern, it's a pretty easy pattern to follow. We can be wrong though. You could say I was a cheat with my deck of cards. That you drew, that I stacked the deck so that you would draw all black cards. But if I had actually had a fair deck, half red, half black, you would have been wrong. So this is called a type 1 error. It's rejecting the null hypothesis even though it's true. This is like convicting an innocent person. This is the one we go out of our way to avoid. Okay? We don't want to reject the null if it's true. The other option, error that you could make, is failing to reject the null hypothesis when you should have. It's called a type 2 error, and I'm not going to mention type 1 or type 2 again. Just if you see them in the book or questions, this is what they're talking about. This occurs when the sample evidence provides support to reject the null hypothesis, or you had enough evidence to reject the null hypothesis and you didn't. So in the case of the deck of cards, you had enough information, your probability was low enough that you probably should have said, no, the deck wasn't fair. Mr. Jones is a cheat. But you went ahead and said, no, I trust Mr. Jones. And you would have been wrong. This has happened. I did this deck drawing thing, and I had a fully loaded deck. There wasn't a single red card in the deck. And the class kept drawing cards. They just like, nope, let's let someone else do it. Maybe someone was luckier. They drew 16 black cards in a row and wanted to keep guessing. I'm like, how many black cards you got to guess before you give up? They just didn't want to think I was cheating them, and I was. Making this error is like letting a guilty person walk free. It's not the desirable one, but it's neither of them are desirable, but it's the lesser of two evils. So we're going to have, they assign probabilities to these errors. Alpha goes with type 1, rejecting H0 when it's true. And beta goes with type 2. It's rejecting H0 when HA is true. So this level of significance, alpha, is the probability of making a type 1 error. And I think I'm out of slides, so let's go to the board. Share screen, share all. There we go. Let's start talking some stats. What is this alpha shit? So you remember how I've been telling you the whole semester 5% is considered unusual. This is the default alpha we use. Default alpha. That's alpha. Maybe I'll write that up here. That's a big old thick marker. This color. The default alpha we use is 0.05, which makes beta 1 minus that, which is 95. Or that's 5%, and this is 95%. Okay? This is the alpha we use for hypothesis test. Alpha is for hypothesis tests. And oddly enough, beta is for confidence intervals. I'm saying that right? Yeah. Yeah, beta. No, I don't know that that's beta. I don't want to say that's beta. Beta is the other one. If we do 1 minus alpha, though, and we multiply it by 100%, we would get, let me say it this way. I like this better. This is better. We get 0.95 times 100, which is 95%. That's what we use for our CI. Okay? And we'll see this when we start doing some hypothesis tests. You will see, and I'll show you. We'll do confidence intervals and hypothesis tests and show you how they match up. When alpha is 0.05, our confidence interval is 95%. This is kind of like the regular one. This is the default, I said. We could be less strict, have it higher, where the confidence interval is only 90%. So this is like strong evidence. So CI. So the evidence against the null try this again. I'm trying to do this all in one area. Evidence against H naught. I'm going to do it in this column here. When we have alpha equals 0.05, we have strong evidence. This is less strong. When they go alpha equals 0.01, give a little bit more room when I write. The CI is 99%. This is considered very strong evidence. And when alpha is 0.001, this is like 99.9%. It's overwhelming. There we go. And I'll pause for a second and let you write that because I know you're not on slides anymore. I think maybe I should clarify something else further, but I'll let you finish writing this first. Okay. This 1 minus alpha times 100% confidence interval, that is for the two-tailed tests. Where HA has the parameter that is not equal to. So if we had like alpha equals 0.05, and we're getting 95% confidence interval. In terms of the confidence interval, we have 95% here. There's 2.5% left on either side. For the one-tailed tests, oh, let me change color for this one. It's brown work. This is where HA has either a less than or greater than. Instead, we use 1 minus 2 alpha. Okay. So 0.05 alpha is our standard. If I plug that in, I have 1 minus 2 times that. I end up getting 0.9. 0.90 times 100% is 90%. So here we have our confidence interval. This is our range of our confidence interval. 90% here, and then we have 5% on either side. Put brackets right there. And I'll show you this more. Once we've done hypothesis tests and we're comparing it to confidence interval, this will make some more sense. But I think if I say it enough times, it'll really, really stick. That's good. I'm already done with 10.1. We are so getting to 10.2 today. Actually, I got one more thing I want to say in this section. We'll get to that. Let you finish writing this. If you need this up longer, let me know. So this alpha thing, this level of error, that we want to avoid. You want to avoid making a mistake. So that actually plays into how we pick alpha. We pick alpha based on how important it is to not get this wrong. Okay. If you were doing statistics on stocking a vending machine, if you're doing stats on this, a mistake isn't the end of the world. Okay. So we could go with alpha equals 0.05, but that's fairly strong evidence. You might want to taper it off a little bit. You might want to do 0.1 or 0.15 or 0.20. You have more room for being wrong, but you'll be more precise in the results if you're right. On the other hand, let's say you're doing open heart surgery. Is 95% really good enough? Like if you're doing it and you have a 95% success rate, that means 1 out of 20 people are dying on your table. I don't know if that's a good success rate. I don't know if I would be happy going under open heart surgery if I was told there was a 5% chance that it failed. Unless I was going to die without the open heart surgery, and then it's like, all right, whatever, anything you're doing to save my life. But you know what I mean? I think you feel me. So 0.05 may be too high. For something that's important. You might go downward. 0.01, 0.05, 0.001, something like that. That's the end of 10.1. I don't think I used my slideshow last semester. It really speeds shit up. If I give a copy to the students and lecture with it, I think I'll do this in the future. I like that. That worked pretty well. So I haven't even told you how to do the hypothesis test. We've talked about the results of the hypothesis test, what it really means, but we haven't talked about the steps for it, and that's what 10.2 is. That's what we're getting to. Okay? And if you're ready, I will pull the next slide. If you need it longer, let me know. So, 5 easy steps of the hypothesis test. Step 1. Identify the two claims. And label them H0 and HA. So you'll have like H0, HA, let's say, let's do the stats one again, the test. Mu equals 73. Mu was greater than 73. That's what I mean by identify the two claims and label them H0 and HA. Your pro tip for this, ooh, different thing. Pro tip. Jot down a couple words of what this means. So if I were to do that here, student average is 73%. Student average is higher. Greater than 73%. This part is essential. This part on the right will help you later on. Helpful later on when we're making our statement of conclusion. Okay, step 2 is assuming well, yeah, the assumption is made that data has already been gathered. Okay, so number 2 is find the test statistics and p-value. And I will often abbreviate this as p-val. I say p-val. I'll even say p-val. I don't know why. I'm only saving 2 letters. It seems pretty fucking lazy now that I think about it. But I do it. I don't do p. I never put p because p, just p by itself, because p can be confused for proportion, and we don't want to do that. So we never want to say this is p. This is not proportion. This is called the p-value. Good thing to know about this. StatCrunch will do this for you. And I'll show you as we're doing each section how that works. Step number 2 and step number 3 are kind of interchangeable. It doesn't really matter which one you do first. So step number 3 is identify alpha. Alpha is called the level of significance. I should have told you that in the last section. The problem will either tell it to you, something like that. If it is not given information, use alpha equals 0.05, our default setting. I'm going to do number 4. Well, we can get it here. Number 4, compare the p-val to alpha. There are 2 outcomes here, possible outcomes. A, the p-value is less than alpha. When we do this, we will reject H naught, support HA. And the other option is if the p-value is greater than or equal to alpha. If that happens, we do not reject H naught. And we do not support HA. It's worth noting the do nots go together. And I got a catchy jingle for you. In fact, I'll write it down on the next slide. Ready for another slide? Ready for the jingle? If the p-val is too low, reject the HO. HO being H naught. But it looks like HO. Like ho, ho, ho. Reject the HO. Reject the null. And so P low, too low. If the p-val is too low, it means it's lower than alpha. You reject H naught. If you don't like saying reject the HO, I've had some teachers that say I really don't like that. A variant of this is if the p-val is too low, the null must go. I don't think that sticks in my memory very well. That's the only line you got to remember. If the p-val is too low, reject the HO. Because it's implied that if the p-val is not too low, we don't. And it even matches up, the knots match up here. The p-val is not too low. We do not reject, we do not support. Not too low means it's bigger. Too low means it's less. P-val is less than alpha. P-val is greater than or equal to alpha. I guess I could have written this over here where you have more room. And when we reject the HO, we support HA. That's the only part that's really missing in that jingle. You have to remember it. Because step 5 is our concluding statement. And it's always about HA. So how does this play out? Well, we had two possibilities. The p-val is too low, or the p-val is below alpha. We are supporting HA. And why would we support HA? Because there is sufficient evidence to support the claim that, and then you kind of want to just paraphrase HA here. Sometimes it's already phrased pretty well in the question. Sometimes you just grab the question, the words from the question. Sometimes it's as easy as grabbing a phrase from the question. But remember how I told you to jot down a couple words? We could use that right here. So we're talking about student average for the mean problem. I'm talking about student average is greater than 73%. So for the mean problem, I would say there is sufficient evidence to support the claim and it says student average is above 73%, and that's enough words to make me remember what it was about. The claim was that the computer programs in class help it support the not that claim the claim that computerized statistics help raise mean exam scores for students. And I could be very specific. I could say above 73%. And ready to see the other option? Option B for this. B was when the p-val is not too low. P-val is greater than or equal to alpha. This was do not reject H naught. Do not support HA. Why are we not supporting HA? There is insufficient evidence. And again, paraphrase HA, that computerized stats help raise the mean final exam scores above 73%. So this part is particular to the one example I was just giving, but normally you would paraphrase HA here. And if we're looking at them next to each other, I don't know if I can do this. You slide that camera down. There you go. There is sufficient evidence to support the claim. There is insufficient evidence to support the claim. That is all that's changed in this sentence. Sufficient and insufficient. So you really only got to memorize one sentence format and just change the word. It's sufficient evidence when we're supporting it, and it's insufficient evidence when we're not supporting it. And insufficient evidence when we do not. I meant to say the mean here. I said it out loud. Because it's all about the mean. Not every student scores higher with a computer than they would have normally. Most do. So those are the 5 steps of the hypothesis test. And guess what? This works on every single test. We are going to cover 8 different tests. We will learn 8 tests in this class. There are more than 8 tests, but this is just an introduction to statistics. The only step that ever really changes is the first one. How we label H0 and HA. They're different for each test. But in every case, H0 always has an equal sign. HA always has a less than, a greater than, or not equal. And I'll let you finish processing that, and then we'll look at some examples in 10.2. Like, enough talky talk already, Mr. Jones. What the hell is this stuff good for? You guys ready? All right, so 10.2 is on proportion stats. I'm off the screen because I moved the camera. There we go. 10.2 is on proportion stats. For one sample. So in this particular circumstance, we will have H naught is P equals some value. Some value. HA, P is either less than, not equal to, or greater than. All right, put P down here. That same value. And to do these tests, we do need a normal distribution. Or approximately normal. Just like we did with the confidence intervals. Which means n times p times 1 minus p needs to be greater than or equal to 10. And n needs to be less than or equal to 5% of the population. Other fun things, just recall mu of p is p, our point estimate. Which is x over n. And sigma of p is the square root of p hat times 1 minus p hat all over n. Just like confidence intervals. In StatCrunch, stats, proportion stats, one sample, and then either with summary or with data, depending on if you have the full data set or if you just have the summary. Okay, you guys ready for an example? This is from actual data from last year, last fall. So the math department really wants to make sure we're giving students the education they want in the format they want. So we believe that less than 40% of students want to take stats in a face-to-face course. Which I'll call F2F from here on. This really matters to the math department because although the spring schedule is going up pretty soon for the spring classes, we're scheduling for fall already. So we're coming up with a schedule for fall, and if we have 100% face-to-face classes and no online classes, then we're not representing students' needs. And vice versa, if we have all online classes, what about the face-to-face students? So we kind of need to get the breakdown right. You know what I mean? We want to have enough classes for face-to-face students and enough classes for online. And we can't go too many each because then we get enrollment with like 10 people in each class and the administration gets pissed off. So we don't want that. We want to meet the needs of our students. Okay? So this is pretty important. And we were in a conflict with administration because administration thinks that like 50% or higher want face-to-face. In fact, they would have 0 online classes if they had their way. They have only very mildly recognized that the world has changed since the pandemic and that online classes are a reality that they have to just put up with. But they wanted more than 50% face-to-face classes. So, data was collected in fall of 2021. On enrollment. This is enrollment data. So I'm going to list the class. We looked at Math 21 stats, just a regular course. I'll just put Math 21. If I could spell math, there's an H after MAT. And the other option was 21 with support. Some of my students have a support course this semester. So when we were just following enrollment for fall of 2021, and these were the numbers we got. There were 135 students that opted for face-to-face in Math 21. Online, 550. When we had the support course, the numbers changed a little. We had 254 for face-to-face and 241. So if I get some totals here, total, 135 plus 550 is 685. 254 plus 241 is 594. I get a 0, I get an 8, I get 11. 1,180. Let me just make sure that works. So if I add along the bottom, I got 389 and 791. Does that add up to 1180? Yes, that adds up to 1180. So I'm going to call this W and or WO and W, without support or with support. If we did without support, the total for face-to-face would be 135 out of 685. And that value is 0.197. So 19.7% chose face-to-face. If I look with, we had 254 out of 495. And that's 513. So 51% chose face-to-face for the support course. So these numbers are pretty different. Maybe we shouldn't group them, but let's look at doing an overall grouping. We had 389 that chose face-to-face out of 1,180. So 330. If I went to 3 decimal places. Which means that's my mean, right? My mean is the same as that, so 0.330. If I calculate sigma, remember with that square root formula? I get 0.013685. Let's go look this up on StatCrunch. What do you mean login error? Just loading slow? What's going on here? What the fuck? Wow. Is it down? Okay, let's try going to a different course. That's the suck. There we go. Okay. Okay, let's shrink that back down. So we're going to go stats, proportion stats, one sample, and we have summary data. Let's just do the 389 and the 1180. We're doing a hypothesis test for 40%. And I got to make sure that I change HA because we said less than 40%. So I'm going to write this stuff down on the next slide. I do want to point out something else while we're in Stacker. This is, look how low this p-value is. This is super low. Maybe let's change it to 36%. How about we do 36%? We can change our numbers. We're grown adults. We can do whatever we want. Notice when I change this, it changes this. That works better. We're going to go with 36%. So, and notice it lists H0 and HA. Isn't that pretty handy? That was actually step one for the hypothesis test. And a little note to myself about what this is about. Percentage of students that want stats face-to-face. Step two was to get the test statistic and the p-value. This test stat is the one that says z-stat for this problem. And it's negative 2.1712048. And my p-value is listed as 0.015. Okay. I want to show you where this kind of ties into the normal calculator and stuff like that. So let's go look at this in the normal calculator. And I'm using the mean that we had before. So 0.330. And standard deviation was calculated at 0.013685. And this is the probability that x is less than 0.36. Notice 0.4 isn't even on here. Like if I put 0.4, it's shitty. Let's go back to 3.6 though. See that 0.959858? That is not actually the mean. I rounded on the mean. Let me type in the actual mean. Because I'm getting an error here that's a little bit off. And I want to be able to point out why. Where the hell did my calculator go? There it is. 389 divided by 1180. 29661016. Let me do that again. And enter in the exact value I have here. 136844849. Let's go for some precision. Okay, so I'm getting 0.986. This is pretty close to 1 minus 0.015. It's really close. It's always going to be like that, too. Okay, so that's how kind of like how the normal calculator ties into it. But putting it into the hypothesis test gives you all that information. So we're back over. Shit, did I do that? Let me do that again. Let's do the between. And alpha is 0.05. So I actually want 0.9 because this is a one-sided test. So our 0.33 lies, or 36 lies outside of it, so it's rejecting it. That's kind of the tie-in to the normal calculator. So, back to our stuff. 3, I didn't give you alpha, so we're going to use alpha equals 0.05. Step 4 is to compare alpha and p-value. So my p-value is 0.015 and alpha is 0.05. The p-value is less than alpha. The p-value is too low. Reject the hoe. and support HA. And HA, our statement of conclusion, is we're supporting HA, so there is sufficient evidence to support the claim that less than 36% of stats students want to take the class in a face-to-face setting. And to compare this to the confidence interval, I'm going to go back and edit this test and just click on confidence interval. It is a one-sided test, so we're doing 1 minus 2 times alpha, or 90%. And see the lower limit and upper limit? 0.30715 and 0.35217. Well, we see that right here in the normal calculator. But the important thing to note for a 90% CI, which is what matches this, we have 0.3, the lower limit is 0.307. The upper limit is 0.352. The percentage we have was 0.36, 36%. So it's outside our CI. Which means the 36% is probably wrong. Which means less than 36% works. Those are the steps. What happens if we change it to 33% though? What if we said 33.3%? 1/3. So what if I change this to say P was 0.3333? 33.33%, or 1/3. We see our proportion. The p hat that we calculated was 0.32966. That's less than 0.333. What happens if we do the hypothesis test, though? Let's check it out. Change this to 0.33. And I hit compute. And now our hypothesis test, the z-stat is negative 0.02, and our p-value is 0.4901. And if we compare that to alpha, it's greater than alpha. So in this case, p-value is not too low. We do not reject H0. We do not reject HA or support HA. Which means there's not enough evidence. To support the claim that the proportion is below 33%. Now this trips out students a little bit. Because the value is clearly less than 33%, right? It's clearly less. 32.9 is less than 33.3. The reason why is we can't reject H0 because it's close, is what it comes down to. In this scenario, it's close. 0.333 is a possibility. But our sample didn't support it. Other samples might. That's why we don't reject. When it's close, we can't reject H0 because H0 is a possibility. And we saw that on the confidence interval because 33.33% is right here. So it's a 33.33 makes it a possibility. It's possible. All right, so that's it on 10.1 and 10.2. I do want to show you in the class, if you come over to your course, and we're going to talk about this more on Tuesday, much more in depth on Tuesday. If you click on Files, and you click on Important Documents, you will see Stats Project. Are you a suspect? Click it and download it. This is your project that is going to be due end of November, beginning of December. I forget what date it's in the syllabus. We'll go check it in a second. There's a data set for you to use and work with. And the first, when you get past the preliminary discussion, the first 3 pages, when you start working on the stuff, you'll actually see you can do about half the project already. It's non-hypothesis test before that. We get up to part F is even just normal distributions. This was chapter 7. chapter 6 or part 6 is where the confidence interval starts. You've done that. And then we have a couple of hypothesis tests in here. You're going to go through from the beginning, open up the data set. You can get the information right here. And work with it from there. Well, again, we'll talk about that more on Tuesday, but if you want to work on it over the weekend, this is your where to find it. And if we look at the syllabus, it says when it's due. The project is due on December 6th. So 6 weeks from now. And that's it. That's all I got. You got any questions, Paige or Famalaya? Thanks for bearing with me. Sorry about the start. We still got it done. That's good. Other than that, I am done.